Welcome to Piazza Research. My name is JJ, and in this video, I'm going to dive deeper into my formula for estimating the probability of life existing on other planets. For those of you who have seen some of my other videos, you know that the formula is a product operator applied to various different penalties, and we are going to focus our attention and silo in on one of these penalties and how I am computing its value. Specifically, we will look at temperature. Now, all of these penalties have received a weighting and have been normalized based on how impactful they are on life forming. Whereas pressure and temperature are extremely impactful, maybe geological activity is less meaningful when it comes to the likelihood of life forming. But if we narrow in on the temperature, we see that this penalty is computed by rho of t times psi of delta t. That is to say, the temperature range multiplied by the flux penalty. Now, an ideal temperature range is around 225 Kelvin at the lower bound and 400 Kelvin at the upper bound, and then it tapers off on both sides. One side might be more steep than the other, specifically the cold, so the lower bound is going to be steeper than the upper bound as it begins to slope downward. And then the flux penalty, that is crucial in understanding that whether or not a planet has temperatures in the ideal range, if they're fluctuating 50, 60, 100 degrees in a short period of time, this is very difficult for a life form to adapt to. To visualize this further, I have here a graph of the ideal range with temperature on the x-axis and our penalty output on the y-axis. And to be even more accurate, I have here Desmos showing us all of the different terms and how the graph would actually look with our various different sensitivity factors called K, K2, and K3. And then we have A, which is representative of our flux. And so if I run the animation, we can see that the flux, as it increases either negative or positive, it reduces our penalty, which drives our probability of life being there lower. And so this is just a great example of one component of our formula, and I hope to see you guys in the next one. Take care.